In our last video, we saw how the tangent line where it touches the curve is going to be equal to the slope of the curve at that point. Now to find the equation for the tangent line, or more specifically the slope of the tangent line at a point of interest on a curve, we're going to need this concept of secant lines. A secant line is a line that crosses the function twice or more. We're going to focus on the case where it crosses the function twice. Looking at the slide on your screen, you can see that we've got a function drawn with on a graph with grids. And so we could label the function f of x. And if you know your functions, you know that this is probably a quadratic function. Now we've been given two instructions. The first instruction says to draw a secant line through the coordinates 2, 12 and compute the average rate of change. I'm going to add another coordinate, and we're going to have the secant line go through 2, 12 and also 5 and 15. So we want a secant line that's going to go through 5, 15 and 2, 12. And there I've drawn little circles on the graph to illustrate where we want the secant line to pass through. Now let's go ahead and draw our secant line. Like so. So imagine that it's crossing the 2 points exactly. And what are our 2 points here? We've got 2, 12 and 5, 15. Now we want to compute the average rate of change. What's the average rate of change? Well, that's basically going to look a lot like the slope. And so we can write the equation, the change in y, that's our rise, over the change in x. All right, here we go. So we've got the change in y. What's the change in y? It's going to be 15 minus 12 over 5 minus 2, the change in x, and we get 3 divided by 3, which is just equal to a rate of change equal to 1. And that's how we can use the secant line to compute the average rate of change. We're going to look at the average rate of change from where the secant line first crosses the function to where the second time it crosses the function. Now in part 2, we're going to draw a second secant line. It's also going to pass through the function at the coordinates x equal 2, y equal 12. But this time, the secant line is also going to cross through the function at coordinates x equal 4, y equals 16. I've marked it on the graph. It's actually at the apex, at the top of the quadratic function. So I'm going to go ahead and draw this secant line. Hopefully it'll look all right. And there's our second secant line crossing through the 2 points of interest. Now let's go ahead and compute the average rate of change. We've got change in y, the rise, over the change in x, the run. Change in y is going to be 16 minus 12. Change in x is going to be 4 minus 2. And we get 4 divided by 2, which is just equal to 2. So now the average rate of change is 2. So we drew the second secant. Notice that I drew the second secant in a very deliberate kind of fashion. I drew it so that it also crossed the same coordinates where we're interested in finding the instantaneous rate of change. We're looking at where the tangent line is. Remember, the tangent line intersected the function at coordinates 2, 12. And when I drew the second secant intersecting further to the left of the function, right, further to the left, I guess I've drawn an up arrow there, I could draw it to the left like that, as we're rotating the secant lines to become steeper, these secants are starting to look an awful lot like the tangent line that we drew in the previous video. And so if we keep drawing secant lines, they're going to get very, very close and or approach the tangent line. Make sure I write tangent line, because this here, this is the point of tangency that we're interested in from the previous video. We showed the point of tangency in the previous video. Now let me show you a prepared slide drawn a little more nicely that illustrates these secant lines. So we've got a secant line, we've got 3 secant lines, right, here, here, and here, that are dotted. And as they become steeper and steeper, starting from the first secant line that we drew, we're getting closer and closer to the point of tangency. How can we get the secant line to get very, very close to the point of tangent, or to the tangent line, excuse me? How can we get the secant line very close to the tangent line? Well, mathematically, algebraically, we can use this idea of limits. Again, this idea of using limits so that we can make the change in x infinitesimally small. Notice that the change in x was getting smaller and smaller as the secant line was getting closer and closer to the tangent line.